Okay, we're back for some physics problem solving. We're still working on forces, and I wanted to do a problem involving Newton's third law. Okay, so this is kind of a classic problem. You can imagine a situation where you have people pushing against each other. Okay, so let's suppose a group of physicists meets a group of engineers in canoes out on Lake Michigan. After a friendly visit, trading nerdy jokes, a person in the first canoe pushes on the second canoe with a total force of 146 newtons, and the push is ultimately going to separate the two canoes. And the total mass of canoe 1 and its occupants is 150 kilograms, and the total mass of canoe 2 and its occupants is 250 kilograms. And the two things we'd like to know is, what acceleration does the push give each of the two canoes? And what is the separation of the canoes after 1.2 seconds of pushing with whatever acceleration we find in part A? Okay, now the trick with using Newton's third law is that you introduce a new step into our problem-solving strategy for forces. So we still start by drawing free body diagrams for each canoe, but instead of immediately jumping to Newton's second law, we think about Newton's third law to start with. And the reason we do that is because there will be forces that appear on each of the two free body diagrams that have equal magnitudes but point in opposite directions. And so we need to know what those are before we implement Newton's second law. So then we apply Newton's second law, which we'll use to find the acceleration. That's our standard practice with forces. And at that point, once you know the acceleration, then you can go back to doing what we've been doing all along this semester, which is using kinematics. Okay? So let's go ahead and do the first part of that. We'll get to the acceleration, and then I'll let you go on and do the kinematics problem yourself. Okay, so in this case, I'm going to start by drawing free body diagrams. And the free body diagrams, there's two of them. There's one for each of the two canoes. So I'll call those 1, 2, and 1. Okay, so what are the forces acting on all of these canoes? So there's always the weight of the earth on canoe 1. There's the weight of the earth pulling on canoe 2. And I know the masses of the canoes, so I can compute the values of those weights. There is clearly a normal force. We'll call it the normal force of the water on canoe 2, and a normal force of the water on canoe 1. When we study fluids next semester, we'll learn that that normal force is actually a force we call buoyancy. And then there's the force of the push. Okay, so I'm going to call this the force of canoe 2 pushing on canoe 1, and then canoe 2 experiences in the opposite direction a force of canoe 1 pushing on canoe 2. And the whole point in labeling things the way we do is so that life becomes easier when we get to Newton's third law. One of the things that we've always stressed is that when I draw a free body diagram, the second index on every force on that diagram better be the index that describes the object that I'm talking about. Over here, similarly, I'm talking about canoe 2, and the second index on each of my forces is 2. Okay, now Newton's third law is that for every force, say the force of canoe 2 acting on canoe 1, there is an equal, that equal means equal in magnitude, force, that is the force of canoe 1 acting on canoe 2, that points in the opposite direction. Okay? So you'll see here the index structure and why it's useful. The Newton third law pair to this force that is on the free body diagram for canoe 1 is exactly the same force with the indices reversed. And so if I reverse these two indices, what I see is I'm looking for a force on canoe 2 that came from canoe 1 and points in the opposite direction. So if I go to my free body diagrams, I see that F21 points to the left, and so the Newton third law paired to that better be a force pointing to the right. And if I go to the free body diagram, indeed I see there is a force pointing to the right that is the equal and opposite Newton third law pair to this force pointing to the left. And so, as is my habit, I will put a little hash mark on those two forces to indicate to me that they are indeed third law pairs. Okay, so that's Newton's third law. And so now I can go on to Newton's second law. Now, the canoes are not accelerating upward, so I'm going to completely ignore the up and down direction. I don't need to solve that problem. Let's just focus on the horizontal case. And indeed, what we know is that Newton's second law says that the sum of the forces in the x direction better be equal to the mass times the acceleration in the x direction. Well, if I look at my free body diagrams, what I see is that there's only one force pointing in the horizontal direction for each of these two canoes. And so for canoe 1, I can write that the force that canoe 2 exerts on canoe 1 is equal to the mass times the acceleration that canoe 1 experiences in the x direction. And for canoe 2, I see that the force that canoe 1 experiences, or that canoe 2 experiences from canoe 1 is equal to the mass of canoe 2 times the acceleration that canoe 2 experiences. Okay, so if I solve each of those for acceleration, I see that the acceleration that canoe 1 experiences, let me just put an x there to be explicit, is equal to the force that canoe 2 exerts on canoe 1 divided by the mass of canoe 1. And that's equal to 46 newtons divided by 150 kilograms, or the acceleration is 0.31 meters per second per second. Okay, now this is in the negative x direction. Okay, now I did something very bad, which is a bad habit that all of us have, which is I haven't been clear up here at the top about what my plus and negative directions are. So let me indicate now that that's the plus x direction, since I'm going to make that assumption. And so at last I have the acceleration that canoe 1 experiences in the x direction is minus 0.31 meters per second per second. Now, that choice of plus x and minus x is completely arbitrary. All that matters is that I'm consistent in the choice that I make. So when I get to doing the kinematics part of that problem, this sign is going to be important. Okay, so similarly, if I go back to my Newton's second law for canoe 2, I can solve that for the acceleration that canoe 2 experiences in the x direction. That is going to be in the positive x direction, because that's the direction that the force in the x direction points. So this is the force that canoe 1 experiences from canoe 2. I divide it by the mass of canoe 2. And now this is the point where I experience or I use the information from Newton's third law. Newton's third law says that the forces are equal in magnitude but pointing in opposite directions. And I know that the magnitude of the push was 46 newtons. I divide that by the mass of canoe 2, which is 250 kilograms. This is going to be in the positive x direction, okay, by design and construction, and that jives with my assumption that this points in the opposite direction as that force. And so if I numerically work that out, what I find is that the acceleration experienced by the heavier canoe is 0.18 meters per second per second. So A2 in the x direction is plus 0.18 meters per second per second. Now at this point, I like to try and look at my answers and convince myself that they're right. Okay, and so there are two things I can check. First of all, I can check the directions, and one canoe is accelerating to the left, and the other canoe is accelerating to the right. That's exactly what I would expect to happen if two canoes pushed off of each other. And then I know that this canoe, canoe 2, is heavier than canoe 1. Okay, it weighs 250 kilograms, whereas canoe 1 massed 150 kilograms. And so, does it make sense that the acceleration of canoe 2 is less than the acceleration of canoe 1? Sure, that makes perfect sense. It jives with our common everyday experience. When heavy objects are pushed on by small objects, the heavy objects accelerate at much smaller magnitudes of the acceleration. So this again jives with exactly what we would expect. So the last part of this problem, which I'll leave for you to do on your own, is the kinematics. And in this case, we've used the force problem to tell us what the initial conditions are, namely that the acceleration experienced by canoe 1 is minus 0.31 meters per second. The acceleration experienced by canoe 2 is plus 0.18 meters per second squared. We're told that the acceleration happens for 1.2 seconds. And then the assumption that you need to make, the thing that you need to impose on the problem, is that when the push started, the two canoes were at rest. And so the initial speed of canoe 1 is the same as the initial speed of canoe 2, which is 0 meters per second. Okay, so that should be enough information for you to work out the kinematics of the problem the way that we've been doing for most of the semester up to this point. Okay, so that's a problem involving Newton's third law. Good luck, and we'll do some more problems soon.